Hello everyone, welcome back. In this lesson, we will learn how to pre-process Landsat 8 Collection 2 Level 2 imagery before performing any remote sensing analysis. This is one of the most important steps because raw satellite imagery contains clouds, cloud shadows, and atmospheric effects that can significantly reduce the accuracy of our results. So let's begin. So we'll begin by creating a function called mask layer that named as a mask LH9SR. Inside this function, we have used a QA pixel band. The first thing we do is to access the QA pixel band. The QA pixel band is actually that stores information about the clouds, cloud shadows, snow, cirrus, and other unwanted pixels. So that's why we are using it. So we use the following line here is the binary represent the first 5 quality bits using bitwise AND operation. We identify pixels affected by the clouds and cloud shadows. So that's why we're going to use this. And only that pixels that are equal to 0 considered as a clean observations. So we are choosing QA pixel and then we are saying that represent the first 5 quality bits, and this will identify the affected pixels that are affected by the clouds and cloud shadows. And then we are saying it that the pixels that are equals to 0 show me that. So that's how it's gonna work. Okay, in the next step we remove those saturated pixels like the QA rad set band. Okay, in the next line, we remove the saturated pixels. The QA rad set band identifies pixels where the sensor became saturated due to excessive brightness. So we're going to use this to remove the pixels that became saturated due to excessive brightness. So removing these pixels improves the quality of our analysis and somehow. Okay, in the next step, we scale the optical bands like Landsat collection to store reflectance values as integers rather than decimal reflectance. So to convert them into an actual reflectance values, we use this multiplication and addition function. So this converts the digital numbers into surface reflectance values between approximately 0 to 1. It's from 0 and it's maybe 1. The thermal band ST. Here is another operation or another variable in Google Earth Engine. So that comes the thermal bands. The thermal band ST band 10 is stored as a scale Kelvin value. So we convert it using multiply it with this value and adding with this value. So what it's gonna do is this line. This produces temperature in Kelvin. Since most studies require Celsius, so we subtracted it with minus 273.15. So finally, we replace the original bands with the scale bands and apply both masks. Now, every image entering our analysis has a cloud removed. If they have any cloud shadows, they'll removed, and if they are saturated pixels, they're gonna remove. If they are optical bands converted to reflectance, and then thermal bands converted into degree Celsius. So this pre-process step is essential before calculating any indice you're gonna do or any other environmental indice. So this is the most important step to do for the Landsat 8 imagery or any Landsat series. Okay, so now we have created our pre-processing function. And let's use it to prepare Landsat imagery for analysis. And we begin by importing the Landsat collection to level 2 dataset. So here is the dataset that we're going to use. And image collection is simply a collection of satellite images acquired over the time. So next we limit the collection to our study area. We apply filter bounds to restrict it to our study area, that is region of interest that I have defined over there. This ensures only load images intersecting our region of interest. So after that, we specify the analysis period, and that period is only images captured within time range will be included. And next comes the most important pre-processing step. And what is it? The map function automatically applies our cloud masking and scaling function. Like this cloud masking and scaling function to every single Landsat image in the collection. Like it's instead of processing images one by one, Earth Engine perform the operations across the entire dataset. So we can inspect the process collecting uh, using only we can inspect the processed collection using this. So the console display the number of images, acquisition dates, metadata, available bands, and everything. However, we usually don't want to analyze dozens of images individually. Instead, we create one representative images. So for that, we create a median function over here. So the median composite calculate the median pixel values across all images. So this method effectively reduce any remaining clouds, contaminations, or produce a cleaner, more stable image. So after all of that, the result is a single cloud-free composite representing the selected time period. Okay, this composite becomes the foundation of all the subsequent analysis, including vegetation, water, or any other analysis you're gonna do. Okay, so now we are going to calculate the normalized difference water index using Google Earth Engine. So NDWI is one of the most widely used spectral indices for detecting and mapping the surfaces of water bodies such as rivers, lakes, and ponds, wetlands, and flooded areas. It enhances water features while suppressing vegetation and build up land, making it an essential tool for hydrological and environmental studies. So I will explain the complete code line by line, discussing why each step is important and show you how to export the final NDWI map as a geotiff for further analysis in GI software. So let's calculate NDWI. Okay, so first of all, we have created a variable that is NDWI, and we have selected a Landsat, and from Landsat I've selected the band 3 and band 5. So band 3 is the green band. So band 3 is the green band. Water surfaces reflect green light relatively well, so making this band particularly useful for identifying water bodies. And then we have used the band 5 and we are subtracting it. So water strongly absorb near infrared radiations while vegetation reflect it very strongly. So by subtracting the near infrared band from the green band, we can effectively separate water from vegetation and other land cover types. Now we are dividing the difference by the sum of green and near infrared bands. This normalization creates the normalized difference water index, allowing the output values to generally range between -1 and +1. So normalization also reduces the effects of varying illumination conditions and make the results comparable across different dates and locations. So at this point, we have successfully generated NDWI image. So now we have created another variable that is NDWI clip. So we are using our operation named as a clip to clip that into our region of interest. So that's why we have calculated so NDWI clipped is the image that we're going to use further. So we are here defining some of the visualization parameters. We have defined the minimum and the maximum value for NDWI water index and some of the palettes, like how it will look into the map. And then we have a operation map.add layer, like we are adding our operation into the map, as you can see here. So this is the function that will add NDWI into the map. We have used another operation that is export.image to drive, so that we can export our image directly from Google Earth Engine to drive. So what image we wanna export is NDWI clip. Here is that image. We also give it description, that is NDWI. We can also make changes to that name, NDWI 2020 maybe, or anything you wanna do. Then we have a scale. The scale is same as that of the previous data set that we have used. The Landsat scale is 30, so we are also using scale 30 here. So we have the region of interest that we have defined the ROI. Then we have a file format, that is geotiff and maximum pixel 109. So increase max pixels to handle the larger export. You can also do larger exports uh, if you have a larger area. You can maximize it, like you can make it 1.4 or 1.5, and you can increase it. But my area is not that big, so I'm giving it 109. And when I run it, it will show me. It will also show here and also here. So this is NDWI. The lightish areas are watery and the darkish areas don't have any water. So high positive values generally indicate a river, lakes, and reservoirs, wetlands, and other surfaces of water bodies. And the values near to zero usually correspond to vegetation, urban areas, bare soil, and other non-water surfaces. So it's important to remember that NDWI identifies surface water based on its spectral characteristics. So that's how we calculate normalized difference water index in Google Earth Engine using Landsat 8 imagery. I hope this step-by-step explanation helps you to understand not only how to calculate NDWI but also why each line of code is important. If you found this tutorial useful, please like the video, subscribe to the channel, and turn on the notification bell so you don't miss upcoming tutorials on Google Earth Engine and remote sensing, GIS, and Earth observations. In the next video, we'll continue exploring another important remote sensing index and learn it how to apply to the real world environment and urban studies. Thank you for watching. I'll see you in the next tutorial. Bye.